R. Okay, just for closing this part in quantum mechanics, we close with the quantum harmonic oscillator. The harmonic oscillator, you see the whole time, everywhere, the pendulum. Dun, 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 that's harmonic oscillator. And you have seen that in the school. A string moving between, you attach a block with one string one side, one string the other to a wall and move it, and it will move like this. No? If the oscillations amplitudes are small, that's a harmonic oscillator. The harmonic oscillator classically follows these equations here. I hope they can be seen. I don't know if in the image they will appear correctly, but this is clearly cosine of omega t sum. This is an oscillation. When you see cosine of sine, there is always an oscillation. Cosine of sine, they give the same oscillation. The difference is a shift of 90 degrees between both functions. So that's not a... And this is the energy of a quantum harmonic oscillator system. This is the kinetic energy, 1/2 mass velocity squared plus 1/2 kx squared. This is the potential energy. Potential energy, 1/2 k squared. This same energy you will convert into quantum mechanics Hamiltonian. So you have to convert this kinetic part, as we did before, in the kinetic energy, but in the sense of quantum mechanics, and this potential energy is the same. Well, we can do that. That's not a big deal. The Hamiltonian, of course, of this system will be p squared 2n minus or plus 1/2 kx squared operator. And of course, a Hamiltonian acting over a wave function in position space will be minus h squared 2n second derivative. Let's assume that the harmonic oscillator is in one direction because it could be in 3D. It could be 3D, but it doesn't matter if you understand one dimension. Plus 1/2 kx phi. Remember, the operator position applied for the wave function in position space is just the position itself. And this is the Hamiltonian you will solve. Okay? And this is equal to energy times wave function. We could repeat the same process as before, but this problem is not that easy to solve. So I will not solve it here. Whoever wants to go deep, go to the textbooks, especially Griffith's quantum mechanics, I recommend, and so on. But the quantum harmonic oscillator is so important because we're using quantum field theory. The way how we quantize the quantum fields in quantum mechanics. We do it by using the algebra of the quantum harmonic oscillator. So we go down. Look, this is how the energy behaves in a quantum, not in the quantum, in the classical system. Let me delete this. This is the energy, no? As a function of the distance. Yeah?
You're not supposed to write on the board anymore.
Why not? I can delete it. Okay.
It's just, you see the warning in the bottom.
Oh, yeah. Just ignore it. Assume that you didn't see anything.
You didn't see it.
Okay. Then, yeah, I will don't write anymore. So this is the energy as a function of the distance. What happened is that once, what happened here? Well, this is the potential energy, actually, not the total energy, only the potential. The total energy of the system, of course, is conserved. It will be a constant. So what I'm telling you is that when the amplitude is maximum, the potential energy is maximum, the kinetic energy is zero. Here, the potential energy is zero, the kinetic energy is maximum. And here, the kinetic energy again is zero, but the potential energy is maximum again. Well, of course, it's oscillating in the other extreme. Then, if we go down, quantum mechanically, this is what I was writing to you. This is the Hamiltonian. This is the potential energy. And this is the Eigenvalue problem. At the end of the day, when you solve this problem, you find that the energy levels follow this equation. Yeah, you cannot write here. They follow this equation. This equation is telling that the energy levels is equal to n. N is the particle number operator plus 1/2 h bar omega. Then let me put this board here because I would like to write a few things. Yeah, let's put it there. Yeah. This. Vamos, maldita tablero. Let's say something bad in Spanish. Okay, this is n. This n in operator notation is a daga a, where a is an annihilation operator, which annihilate particles, and a daga is something which create particles. Okay. These are operators, and the definition is when they appear, for example, A, if it operates, it annihilates the vacuum. When A appears, is applied over the vacuum state, it gives you 0. But if it's applied in a non-vacuum state, for example, there are n particles, let's say 5 particles, this operator annihilates 1 particle, then remain 4 particles instead of 5. And this one creates particles. But when you combine them in this way, this is the particle number operator. So when n operates over n is just n, is the particle number operator. Annihilates and create after is the particle number operator. And these operators follow some algebra. Commutator A daga is equal 1 in the quantum harmonic oscillator, and this will be important at the moment of doing quantum field theory, quantizations, and so on. They use this algebra. The difference is, of course, we are dealing with quantum fields instead of a single particle. But the idea is the same. When n is 0, it means there are no particles in the system. For example, you have a system of photons which obey the. So if you annihilate all the photons, there is nothing, and still the vacuum has energy. 1/2 h bar omega. And this is the source of the dark energy in relativity, for example, or vacuum energy itself in the Casimir effect and all these kind of issues. So it's very important. The wave functions in this case are very complicated. They use the Hermite polynomials, blah, blah. So I will not emphasize in that. I will emphasize in this. This is the energy. Look at the classical curve of the potential energy and look at the wave function, how it behaves. When the energy is 0, when the energy is 0, no, when the particle number is 0, the energy still is finite. The energy of the system is finite. Still, of course, if you have, let's assume that you have some hypothetical particle following the quantum harmonic oscillator behavior, not a bunch of photons, as I just said. What will happen if the vacuum energy of the quantum harmonic oscillator is 0? I would violate the uncertainty principle of Heisenberg. So in reality, the reason why the energy is different from 0, even at the ground state, is because this is the consistency with the Heisenberg uncertainty principle. I will explain why. Let's assume you have a mountain here, you have a valley here, and you have a particle oscillating here between these 2 points, going and backward, going. And this is x equals 0. If the energy of the ground state were 0, then this particle will just locate here at the origin, and that's it. But what happened? I know the position, and I know the momentum. This is a violation of the Heisenberg uncertainty principle. So what the harmonic oscillator does is that in order to satisfy the Heisenberg uncertainty principle, the ground state of this particle must have some energy, and this particle still move somehow. So such that you don't know the position yet, and you don't know the position. You know partially one or the other, but not both simultaneously. And that's why the ground state has energy.
said that to reach 0 Kelvin is impossible.
Well, that's a different story. But let's say because that 0 Kelvin you mentioned is in thermodynamics, and that's good. Good. There might be some relation, but let's say is the essential idea is different. Is because are different systems anyway. But it's true that some systems, some elements, for example, when you increase the temperature, the oscillators of the system can start to move faster. When the temperature decreases, the oscillators move slower. And when the temperature reaches zero, even at the zero, the oscillators have to move a little bit in order to satisfy the Heisenberg uncertainty principle. So, I mean, the idea is that you cannot violate the Heisenberg uncertainty principle, and that's why the vacuum has energy. The ground state of the quantum harmonic oscillator has energy. And then, let me see if I put to record this because I forgot if yeah, it's recording. And knowing this, of course, when you quantize quantum fields with this algebra, you find that the ground state has an infinite energy. But then after you make a cutoff in relativity, and you find the problem that the vacuum energy is 120 zeros to the right, larger than the theoretical value, the experimental value we observe due to the expansion of the universe. And that's the problem I solved in the last paper I told you. And then I found the way to solve. I think it's correct. That I am 99% sure that that's the solution. The question is how long it will take for people to recognize it. That's the big issue. But I am almost certain that that's the solution because it's the simplest solution. And normally the simplest solutions are the correct. When you start to invent things and these Marvel stories, Doctor Strange, the possibilities of success are lower. I mean, Marvel and Doctor Strange might come is when you need it. It's like when you need a hero. But as far as you don't know it, and you can use simple arguments to solve a problem, you should attach to those simple arguments as much as you can. Because we have to start with something which is true for finding the solution or something. But if you start from something which you don't know if it's true, and you start to extrapolate, and that's what happened to the persons with this supersymmetry. Supersymmetry between 2000 to 2015 was the fashion, the boom. Everybody wanted to do supersymmetry. And what happened? Nobody found supersymmetry in the accelerators. Everybody stopped doing. And the question is why so many people follow that idea? Who in the hell talk to people? Hey, for collective behavior. No, that would be a research topic. Why people really start to follow some research topics because they look marvel. No, they look like wow, super. It sounds beautiful. It sounds smart. But at the end of the day, we have to attach to the simplest ideas first, and then after is when you have to start to look into if you need it, if you really need to go to. Okay, well, these are the energy levels of the harmonic oscillator 1, 2, 3, 4, and this is how the wave function behaves. You can see 1, 2, 3, 4, 5. Or let's put 1, 2, 3, 4. 4 zeros has this wave function with n equal 4. N equal 3 so 1, 2, 3. N equal 2, 1, 2. N equal 1, only 1, 0. And n equal 0 is always positive at the center. This is the behavior of the wave function, but the probability is the square, is proportional to the square of this function. So it will be positive. The probabilities are always positive. Remember that. This closes quantum mechanics. And then I will start the video now because I will explain a little bit relativity, which is the last 30 minutes of this class.